It seems like
The lines are very thin here.
Okay. It seems like you could boost check, now it seems like these image tags are good enough you could.
So it looks better on a small image like this. If you blow up this image and you see this like huge broad edge, it doesn't look as good.
Okay.
Right? It looks better when it's shrunk down.
Yeah.
This does look better when you blow it up.
Oh, okay.
Yeah. This is sort of a probabilistic. It's average over multiple predictions.
Yeah.
Yeah.
Can I talk more about how they choose the queries and why they choose those queries?
Again, I don't want to say too much because I'm not an expert on computer vision, but my understanding is that one of the biggest signals in vision processing systems is gradients, like changes in the color, right? Changes in the intensity. And so that's why the query set is a query set of gradients over the gradients of the image patch. Yeah.
So if it knows gradient is like, or like if you can sort of predict that gradient and like color can be a feature, like couldn't you do it like unsupervised as well?
Only if you know which gradients actually map to edges. By saying gradients are important, I'm just saying some subset of the gradients are used to map to
Couldn't
edges.
you try like different parameters and just see what?
But if you don't have the ground truth, how do you know if you're doing well or not?
So like if you, I guess like you could just look at the output and give feedback.
Okay, so that is still ground truth, but it's more of an interactive machine learning problem with human in the loop. Right here it says we pre-collect the training data. Right. Either way, you still need supervised labels.
Well, wouldn't a human be way faster, clicking yes or no on like, oh, this is good or this is bad then?
I'm teaching a special topics course called Interactive Machine Learning in the spring. You're welcome to take it, and we'll talk about these issues and other issues. But for this class, we're just do offline supervised learning and offline unsupervised learning. But your point is valid, and it's the answer is it depends. Yep.
What are the coordinates work for?
I'm sorry.
We have built some coordinates before.
They're for clustering the late training labels. So here, if I somehow knew that these were orange labels and these are blue labels, right? Then I could use the standard definition of entropy and information gain, or multiclass Gini index, to compute how good this split is, right? In order to assign these image patches to clusters, I need a coordinate system.
So the coordinate just like in this slide, just like color
The coordinates are basically you compare pairs of pixels, and then you assign a value to that coordinate depending on the comparison of that pairs of pixels. The intuition is that related image patches that look similar will have similar coordinates. So, for example, these two image patches look very similar to each other, most pairs of pixels, if you query these two image patches on most pairs of pixels, it'll give you the same answer in the same patch or in different patches, right? For these two, only on a very small subset of the pairs of pixels, at the boundary specifically, would you get different answers, right? And so if your coordinate system is, do these pairs of pixels lie in the same patch, yes, or lie in different patches, 0, then these two images will have similar coordinates. And so if you cluster using that coordinate system, you get a clustering assignment that looks like this. And then use the clustering assignment to compute the entropy. Yeah?
Is this, like, how much better is this than if you just did it without the whole structured decision tree approach? Like kind of the default approach you presented at the beginning? Like, is it a lot better?
It's a lot better.
It's a lot better, okay.
Well, you can do a lot of tricks to engineer a feature representation. And then it starts to be compared. I'll actually show you. So there are versions of CRFs that do pretty well. In fact, these methods, they don't actually, they're at the state of the art. I mean, these are accuracy measures on some test set. They're at the state of the art. They don't do better than the state of the art. However, so this works, this is frames per second, so how many you can process per second, right? This is at half a frame per second. This method is at 60 frames a second, right? No Viterbi, these are higher order, some of these are like higher order CRFs, like second order, third order, fourth order, right? And this is just a sliding window, 60 hertz, right? So there are different ways to measure what is good. I guess.
What's T?
Number of trees, I believe. No. I don't know, actually. I refer you to this paper.
Are the three scores three different like standards?
Measured, yeah. So the right one is average precision. These are different types of overlap scores. Like if you draw a root, because if I just label everything as an edge, somehow like if I label the entire image as black, somehow that's cheap. Yeah. I believe these are different types of overlap metrics where you are more like for or against conservative versus aggressive labeling of edges. Right, if I get the structure right, but I'm broader than the ground truth, is that good or bad? Right?
Yeah.
Okay, so now I'm going to talk about a project that I was a part of in speech animation. And in fact, the approach that we adopted for this project was directly inspired by the previous paper. So we're also going to use a sliding window approach. So this is the problem with speech animation, which is given, I hope the sound works, given a sequence of audio, can we produce a sequence of video that lip syncs to the audio? So this is a sequence prediction problem. If you're interested in seeing some of these videos, they're available on this link. Okay, so hopefully the audio works.
Because there's never been a leak this size, at this depth, stopping it has tested the limits of human technology.
So this is the model that we trained. We took as input some audio from President Barack Obama. And then, let's see here.
Because there's never been a leak this size, at this depth, stopping it has tested the limits of human technology.
Okay, so here's what the training data looks like. We took this guy, he's an actor, his name is Ken. And we recorded Ken speaking about 2,500 sentences, so about 10 hours of speech. He just sat in front of a high-def tracking camera for 10 hours. He was paid very well. And so we built a model using standard computer graphics methods of his lower face. And then the training data basically is the X is a phoneme sequence, a phonetic sequence, frame by frame at 30 hertz. And the Y is a frame by frame sequence of configurations of his face. So his face has, in the simplest version of his face model, it has 30 degrees of freedom. So at every frame, you're predicting 30 numbers. In the edge detection paper, at every frame or every sliding window, you're predicting 16 by 16 patches. Here, we're predicting 30 real value numbers, which map to a configuration or parameterization of his face, like how wide open or how skewed the mouth is. So that's the training data. Here's the prediction task. So X is a sequence of phonetics. Y is a sequence of outputs. Capital D here is 30. So each Y in this token sequence is a third-dimensional configuration of the Ken's lower face. And then we want to run this sequence mapping, right? Okay. So this is the phonetic sequence for the word prediction. The first dimension of Ken's face model corresponds to how wide open his mouth is. So a large positive value in the first dimension, so the first dimension of this, corresponds to the mouth being wide open, and the negative value in the first dimension corresponds to the mouth being closed. So as Ken starts to enunciate the first consonant, the mouth sharply starts to open, and then closes gradually, and then at the K enunciation, sort of has a hinge, and then slowly closes again. So what are some properties of this prediction problem? It's a sequence prediction problem, right? So you could think about doing this prediction, X to Y, using a conditional random field. Well, the first one is that the temporal curvature over time, it can vary very smoothly or sharply, right? So for example, here, the curvature is very sharp, and somehow this curvature is smooth, and it's smooth across multiple frames. Right? So this is not something that you would imagine being able to model easily using a first-order conditional random field. Furthermore, when you make the observation again that there's sometimes seems to be minimal long-range dependencies. For example, how you say the word, or how Ken would say the end of the word prediction, is more or less the same as how Ken would say the end of the word construction, election. You know, you pick a word that has the same ending, right? Any word, it seems to be more or less the same way, and so somehow there's no dependency between the first part of the word and the last part of the word. So again, we have these same two properties as in edge detection, right? We have strong local properties, where we need to model arbitrary local curvature over multiple frames, which is not something that's well modeled by first order linear chain models, because these only model like pairs of frames at a time, where this curvature clearly evolves in some way over multiple frames. Right? And so just to sort of visualize this, since it's a very visual problem, here is the strong local curvature property in action. So here is the phoneme k, and here's all the different ways Ken says k surrounded by different syllables. So each of those lower face configurations would correspond to a very different configuration in our face model, or a very different set of 30 numbers. But they're all the same phoneme, right? And the reason why they're very different is because of the local curvature of the surrounding syllables, induced by the surrounding syllables. Here's a different example.
Due to a unprecedented temperature, a list of activity would threaten our attack to teleport institute or because it contributed to the sick happy tendencies or target birthdays with what happened to that. Very problem lump is take this opportunity to different and don't pattern and hazards and traits into task predicting the link pattern start talking into things they invested in teeth due to having to have necessary here the optimism.
Okay, so keep in mind that every frame, the prediction is done at 30 hertz. Every frame is 1/30th of a second. Right, so if you do linear chain model, it's like I want to model dependencies at a resolution, at just local dependencies at 1/30th of a second, whereas the evolution of this is really it's something that at a much higher, over a longer window. But of course, it's not that long a window, right? We want to model, we don't need to model sort of the entire chain directly in one model, right? Because as long as we can get this local part really well and get this local part really well, they don't really depend on each other. Just like in the edge detection problem. So we're going to use a sliding window approach again. The idea, you take the input sequence, which is an entire sequence, you break it up into sort of subsequences. So this is a one-dimensional sliding window as opposed to a two-dimensional sliding window. We run it through our decision tree, which predicts subsequences of, so here are the sequences of length 5, just for visualization. Subsequences, output sequences of length 5, and then we average it together to get this prediction. This is still, like in the edge detection problem, this is still a fairly complicated problem because it's 5 output frames. Each output frame has 30 parameters, so it's a 150 variable regression problem. So it's still a fairly complicated problem, but it's not sort of exponentially unbounded, the types of issues that we talked about in the previous week. And so this is the only thing that requires machine learning, this inner part. So training, just like in the edge detection problem, the high-level idea is the same. This is our original training data of variable length trajectories. We create a modified training data of fixed length 5 sub-trajectories. We treat it like a multivariate regression problem, and we train a decision tree on this. You could also use a neural net. So what are the query sets? So we borrowed from the linguistics literature, right? So these queries are, the types of queries that you see in the linguistics literature. So we didn't invent anything new. We just sort of read up on the linguistics literature and just create a query set inspired by it. And this is the actual top of our tree. The full tree is about 5,000 leaf nodes. It's fairly imbalanced, a few hundred, I think. I'm not sure. It's not very. It's imbalanced. Yeah.
So all the queries were manually constructed.
We constructed a set of about 3,000 queries. I mean, it's a bunch of rules, and then we wrote a bunch of for loops, right? Enumerating that rule over multiple different frame locations. And then the decision tree, given the training set, automatically decided which rules to use to construct the tree. Running on
That all the rules were manually.
it. That's right. And so this type of manual construction is very easy, right? Because we were learning a nonlinear function from these rules to the output space. If I had to construct a feature representation, a set of rules, where I could trust that a linear representation would do well, then that's a much harder task. Yeah.
Question about like general tagging problem, like this one, how symmetric are these problems? Like, how would you modify this algorithm in order to, like, it puts a video of somebody speaking and then generate what he actually is saying?
I think for that you actually need to use a chain model, like a CRF type model, because the dependencies are much more global.
But if you apply the exact same algorithm you use here, but just interchange the.
So we didn't try it. We haven't tried it. It's a good. We've been meaning to. We have. It's always a million things to try, but I don't expect it to do that well. Yeah.
So, was it that like someone else had done highly annotated speech data and you used that for the actor, or did you also have to go and annotate each individual frame with a
Syllable.
Yeah.
That you can do almost automatically.
Okay.
With modern speech recognizers.
Okay.
Like you talk to your phone. Yeah. I mean, we did clean it up manually, but that's not that much work. Most of it was automatic. Okay, so what does the tree model look like? Well, at the if this is the training data in one of the leaf nodes, right? So remember, we're doing 150 variable regression. So every row is a variable that we're predicting. Every column is a variable we're predicting. Every row is a data point that partitions to this leaf node. The prediction is simply the mean, right? We're predicting 150 numbers. That's the column-wise mean. The training loss. So this is how we split. So in regression, remember, we split by minimizing squared error. It's simply multivariate squared error, where we just we take the prediction of the leaf node, and then we do just a column-wise squared error. Very simple. So we have a query set from the linguistics community. We have a way of making predictions, and then we have a training loss that we're minimizing as our splitting criteria. That's all the ingredients that we need. Yeah.
So the prediction is on like the 30 degrees of freedom, right? And then you construct the image.
Yeah. So there's a face from the graphics community. They built this face model. This face model has 30 degrees of freedom, and we're just predicting within that parameter space. And there's a reconstruction that we don't do. Yeah.
Is there anything about the sort of reverse problem of if you had just the video of his face moving?
You mean lip reading?
Yeah, and then but to synthesize like the audio from that?
Yeah, have you ever seen bad lip reading? So it turns out that lip reading is highly ambiguous, right? The same lip configuration can plausibly correspond to lots of different audio, right? And so now you need something that's somehow semantically coherent. You want a sentence that's semantically coherent. And that requires modeling long-range dependencies.
But the same happens here. You said that different configurations of lip can sort of produce the same sound.
Yeah, so you also need a probabilistic model in some sense too, because you want to model the distribution over possible sentences that this lip reading could produce. I could easily do lip reading of this, and the sentence you get back is complete gibberish, because it doesn't recognize. It's like the cat sat, dog ate what.
I mean, we shouldn't expect to understand what is produced. I mean, we have to have a measure of, the difference between what is produced and the actual, maybe understanding is a different problem.
I disagree with you, and I think most people who's interested in language modeling would disagree that they understand it's a different problem. you have to solve both. It's not a meaningful solution unless you can solve both simultaneously. Okay, so here's another example.
And tonight, I've returned from a trip to the Gulf Coast to speak with you about the battle we're waging against an oil spill that is assaulting our shores and our citizens.
Last example.
And unlike an earthquake or a hurricane, it's not a single event that does its damage in a matter of minutes or days.
So some of the videos are available on this website. Okay, so this is just an example of the prediction at work. Here's a phonetic decomposition of learning. You pipe it through this thing. Here's the actual predictions the tree makes. And then when you recompose it, it goes, so remember the first dimension is how wide open the mouth is, so the mouth is pretty closed. And then it opens up more here, and then it closes again. Starts to close again. There's another one for SIGGRAPH. So it's a little bit, SIGGRAPH is more consonants, so the curvature is a little bit more pronounced. Let's did a side-by-side user study. So we compared our method against some competing approaches. Maybe you guys can take a look. One of these is ours, one of these is a competitor.
Where only one club existed before, he says, two will flourish henceforth.
Play it again.
Where only one club existed before, he says, two will flourish henceforth. Where only one club existed before, he says, two will flourish henceforth.
How many think the left one looks better? And how many think the right one looks better? Okay, so everyone who bothered to vote, voted the left one. That's our method. That's good. So here's we crowdsourced some of this, and so here's some of the results. Higher is better. These are some state-of-the-art baselines. There were 50 test sentences, so.
So you said, how did you ask people to generate this book? Did you do a survey? How did you measure which one's better?
Yeah, we crowdsourced it. So we said, look at these two look at the side-by-side rendering of this animate lip syncing to the same sentence. Which one looks more natural, left or right? And then do randomized blind, the standard stuff. Yeah.
Did you also compare with the actual actor saying?
Yeah, it's right here.
The same sentence.
Yeah. So we have the recording of the actor, because we have the actor's voice, right? So you also record the actor's video.
So there are some people who like your thing over the actual actor saying it?
I mean, it's not, I don't know, it's fairly small. I mean, here's a comparison with the ground truth.
Where only one club existed before, he says, two will flourish henceforth. Where only one club existed before, he says, two will flourish henceforth.
So the one on the right is the ground truth. And as you can see, we're under-articulating compared to the ground truth because our prediction is the average over a bunch of things in our leaf nodes. In order to gain statistical strength and not overfit like crazy, you have to have some amount of aggregation. What does that imply? That implies that we under-articulate. We're not as expressive as the ground truth because we're averaging, we're smoother than the ground truth. Sometimes when the actor is really enunciating, people think it looks worse than a smoother version. And this is just some examples. I think I'm just going to skip this in the interest of time because I'm running a little behind. So the full pipeline is you have input audio. You use standard speech recognition software, such as what's on your phone, to convert it to phonetics. You use our approach to convert it to animation. You use standard graphics approaches to convert it to a cartoon character, if that's what your goal is. It was for our project. And then you could actually take this cartoon character and then you could map it back to what's called a software called Maya, which is like Photoshop for animation. So the animation artist can tweak this animation, like add emotion and stuff like that. Yeah.
So for the reverse, the lip syncing problem, would you still use essentially the same decision tree?
I mean, it's hard to say without trying, but I would say no, probably not.
So like what approach?
I would use something that has a language model built into it. So I can model trend, like semantics. So retargeting is pretty straightforward. It's basically you have this 3D-dimensional representation of this face, you have some dimensional representation of this face, and you just have to sort of find the extremal poses of this face and map it to the extreme opposes of this space, and then it's a linear transformation from one space to another. It's just the matrix transform. So I won't go into the details of that. Here's some results.
If I look funny to you, I may be a chimp, but I'm dressed better than you.
I'm a PhD specialising in computer graphics and facial animation. But at night, I'm a level 10 operative for a secret organisation.
But we are now on different frequencies.
My speech is pretty good, don't you think? Meu português ainda melhor, não acha?
Right, so we can actually, this thing is not specific to English. We can do other languages as well, such as me speaking Chinese.
你们真讨厌，吃饱了喝足了就坐那儿看我说话。
So some people know what I said, other people don't. It's like half the room is really laughing. The other half of the room is like, I'll just play it.
你们真讨厌，吃饱了喝足了就坐那儿看我说话。
You can ask your Chinese friends what I said. Here's a different one, which is my postdoc, Taiwan speaking Korean.
저는 한국어를 전혀 배우지 않았지만 이렇게 한국어로 말할 수 있습니다.
Anyone here speak Korean? All right, you understood that?
Yeah.
It's a little quiet because the audio feed was a little low.
저는 한국어를 전혀 배우지 않았지만 이렇게 한국어로 말할 수 있습니다.
So if you had a phonetic translator that could translate the language into phonetics, and so we did this manually because we didn't have one that did this, then you could use our method to identify. So it suggests that the mechanics of lip syncing is tied to the phonetics and not to the language, which not too surprising. Okay, so now I'm going to spend the last 15-ish minutes just to be a little bit more formal, right, about learning reductions. So the motivation behind learning reductions is that we know how to solve these sort of standard machine learning problems like classification, regression, and there are many toolkits available, which makes this somehow something that you could easily do if you had a problem that was posed in this way, right? And the question is, can we reduce more complicated problems to these simpler ones, right? For example, in speech animation, the reduction is from variable length trajectories to fixed length multivariable regression. Of course, this is still a non-trivial problem, but in a very real sense, this is a much simpler problem than this one. And in particular, this is one that you can solve using an existing toolkit if you had the right transformation of the data. And it bears a lot of affinity to other types of reduction problems you think about in mathematics and computer science. So for example, when people study NP-complete reductions in complexity theory, they try to convert one problem to be equivalent up to a polynomial type transformation to another problem, and then to show that they belong to the same complexity class. Similarly here, you can convert one problem to another problem, and whatever learning theoretic guarantees or generalization bounds you can prove for simpler to analyze problems, hopefully, if you have the right construction, lifts to the harder problem. So there are other learning reductions. So for example, we have binary to multiclass to binary, cost-weighted, unweighted, ranking to binary, sequential to multiclass. We saw sequential to regression, but there's also sequential to multiclass, which is the standard sequential problem of like part of speech tagging. If you're interested, you can sort of view this website, which is one of John Langford's websites. He's one of the people who's done most work on learning reductions. So I'm going to briefly sort of give a formal overview by talking about multiclass to binary. But first, maybe we should ask, why do we even care about multiclass to binary, right? Multiclass seems like a fairly simple problem that we know how to solve well. And the answer is yes, in many contexts, we do know how to solve multiclass well. But nonetheless, there may be some value in sort of understanding how to reduce multiclass to binary. So for example, the conventional approach to multiclass classification is one versus all. You learn a scoring function per class, and at prediction time, you predict the class with highest score, right? There are some limitations of this. First of all, the complexity of this model is linear in the number of classes, which may not be what you want. It's also hard to prove generalization bound. So if you actually look at the generalization bound for SVN for binary classification, it's all based on the margin, right? Which is something we talked about a few weeks ago. Now that notion doesn't generalize in a straightforward way to multi-class classification. So if you want to be very rigorous and have learning theoretic guarantees, this is something that's much harder for multi-class classification. So this is the learning reduction recipe. You're given some original training set. So, for example, Y could be multi-class, or X and Y's could be sequences, right, or images. You create a modified training set, or a set of modified training sets. In the multi-class, the binary reduction, the Y labels are binary. You train your models that you know how to train well, and they're theoretically well justified on these modified training sets. And then your final predictor is some way of combining these that can hopefully preserve the whatever learning theoretic guarantees you have from these H primes. So there's basically two flavors of analysis. The first flavor is error reduction. So if epsilon is the error of H prime, like 0, 1 loss, if it's binary, then if you have an epsilon, which is the error on 0, 1 loss, does that have an implication on the multi-class loss of the resulting H? Usually the answer is something like linear in the number of classes, capital K, times epsilon. Right? So if you can prove that you have this error, and you can prove that this error generalizes, you have a generalization bound, then you can also prove an error of this that generalizes as well.
Yeah. Isn't the scale is like K squared though, as the number of classes?
Depends on the reduction.
Okay.
There are ways to get it so that it's linear in K. So this depends on the construction of the reduction. I could create a complexity theoretic reduction from one problem to another problem that implies exponential time, because the reduction is exponential time, right? Right. So you need a polynomial time reduction. So is there an error? Is there a reduction that preserves this property? No. Does that make sense? Or?
Yeah.
So it depends on the reduction.
Yeah.
And the reduction is basically how you create the modified, smaller, simple problems and how you recompose them. Right. So sliding window is one reduction. Right.
Basically, like, you have rankings, and 5 to 4 to 3. You don't care about 3 to 5. You care about 5 to 4 to 4 to 3. It's like a separation or something like that.
For ranking, yes. This is multi-class.
Yeah, I'm saying if your classes are different rankings, like ranking things 1 to 5, like movies or something like that.
Yeah. Yep.
So for like linear, could you, for example, make like a randomized group of one kind of class, so for example 1, 3, 4, 5, and then like 4, 6, 7, 8, and then run like a couple of those, and then do a trio of them. That would be a way to make.
Yeah, and in fact, did you look at the slides before lecture?
No.
Okay, well, that's actually what the method is. I'm going to present in a couple of slides. I don't believe you. Okay, so the other idea, which is a little bit more powerful in these types of analysis techniques, is called regret reduction. Regret is basically the error of your model subtracted by the error of the best model in your model class. So oftentimes the problem is just hard, and no model gets 0 error, right? But some model gets 0 regret, right? And so if this is sort of the optimal, if this is the best possible model that you can have, a consistent learning algorithm will, when you get in the limit of infinite training data, will achieve 0 regret. And any consistent learning algorithm will not achieve 0 regret in the limit of infinite training data, right? And so if we have, we know how to construct consistent learning algorithms for binary classification, like provably consistent, right? So whatever regret that H hat gets in binary classification does have an implication on multi-class regret. So just an aside on sliding window. So if the base model in the sliding window predictor has 0 error, so the multi-covariate regression